All right, so let's look at atoms. So we're learning about atoms. So if you look at this picture here, this is basically um, kind of an idea or concept of what an atom might look like. And so what we're going to talk about today is how our modern atomic theory came to be throughout the history of humankind. All right, so all the way back in the ancient Greeks, they had these ideas, right? So let's think of this. If I take a piece of aluminum foil and I cut it in half, then I have two smaller pieces. Then if I take one of those pieces and I cut it in half, then I have smaller pieces. And then you keep cutting things and you keep cutting things and keep cutting things till you can't cut it anymore. So the Greek philosophers debated this about 2,500 years ago. Like, what is the smallest piece of something that you can have? They didn't have aluminum foil. They were just talking about different things. In fact, they didn't believe, like they've never saw aluminum foil. That's fairly recent. But there were things that they believed. What if I take this and I cut it in half and I cut it in half and I cut it in half? So one particular philosopher believed that at some point, you're going to get to a point where you can't cut something in half, where it can't be divided. So the Greek word atomos means uncut or indivisible. So the word we use, atom, comes from the Greek word atomos, which means you can't cut it. You can't divide it into something smaller. And a long time ago, Aristotle believed that there were four elements, right? Elements meaning what everything else is made of. And he believed that you couldn't divide these things, right? So he believed that the elements were air, earth, fire, and water. Now, for centuries, people believed that. But by the 1800s, scientists had enough experimental data to kind of support our periodic table of elements. Okay, so they through millennia, they finally came to the conclusion that there's more than just earth, air, fire, and water. One of those people was Dalton. So what's Dalton's theory of the structure of matter? Dalton proposed the theory that all matter was made up of individual particles called atoms. And that word was chosen specifically because of the history. And so John Dalton studied the behavior of gases in air. Based on the way gases exert pressure, Dalton correctly concluded that the gas consists of individual particles. In other words, he had this idea of like what we were just talking about. When the particles hit the surface or the edge of a container, they build pressure. Okay? So Dalton measured masses of elements that combined when compounds were formed. The ratio of the masses of the elements in each compound was always the same. In other words, they were making molecules. And every time the ratio of the compounds were the same and have a fixed composition. So when you burn magnesium, and maybe I'll do that for you guys, it combines with oxygen. Now, in magnesium oxide, the ratio of the mass of magnesium to the mass of the oxygen is always 3:2. Always. So magnesium dioxide has a fixed composition. Now, a lot of that has to do with the atomic structure and how the electrons can interact with one another and bonds and stuff like that takes place, and we'll cover that eventually. But magnesium dioxide always is going to have that ratio of 3:2. So all the elements are composed of atoms, according to Dalton, and all atoms have the same element and have the same mass, and the atoms have different elements, have different masses. Or I'm sorry, the atoms of different elements have different masses. So compounds contain atoms of one or more element. In a particular compound, atoms of different elements are always combined in the same way. Now that's all he knew. Now he wasn't sure about protons or electrons or neutrons. He just said there's this stuff, and when I combine it with this stuff, it's always the same ratio. But what he did do is he made wooden spheres, I always say spears for some reason, spheres, as a model to represent atoms in different elements. A tiny solid sphere with a different mass represents each type of atom. So he tried to put a visual on it. Okay. By the way, I've got a kit in the back, and we'll use those later on this year where we're going to build our own molecules, and it's basically the same as these little wooden spheres. A theory must be explained from the data from many experiments. Because Dalton's atomic theory met the goal, the theory became widely accepted. Over time, scientists found that not all of Dalton's ideas about atoms were completely correct, so they revised the theory and take into account the new discoveries. And that's science. That's science. All the research that I've done up here is built on what somebody else did. That's how science is. You discover things by trying things. You have an idea, you find out if it's right or not. Then somebody after me will come along, and then they'll try to find out if I'm right or not. Sometimes I'm right, sometimes I'm wrong, but we keep discovering new things. So next is Thomson. What contributions did he make to the development of atomic theory? Well, his experiments provided the first evidence that atoms were made of even smaller particles. So when some materials are rubbed, they gain the ability to attract or repel other materials. Such materials are said to have either a positive or negative electric charge. Objects with like charges repel or push each other apart. Objects with negative charges attract or pull together. Amber is a hardened, sticky, kind of very viscous liquid that protects trees from insects and disease. So it's like sap, right? Have you ever seen a tree that has like an orange sap? Well, what happens if a termite tries to eat that tree, it gets engulfed in the sap. Oh, the sap does other things too, but amber basically surrounds. If you look, it almost looks like this is a bug trapped inside the thing. But if amber is rubbed with wool, it becomes charged and can attract a feather. And we'll do some of those experiments too. So in Thomson's actual experiment, and his full name was Joseph John Thomson, he used a sealed tube containing a very small amount of gas at a very low pressure. And then he fired a glowing beam through it. All right? And when he put a positive plate on one side of the glass or tube, he noticed that he could change the beam. So this beam somehow, for some reason, was attracted to the positive plate. Interesting. So when the current was turned on, the disc became charged and the glowing beam appeared in the tube. So if you go back, he had a source of the current, but it wasn't always turned on. So this is what it looked like with the current off, and then when he turned it on, what it did is it charged this plate to be negative and this plate to be positive, and then that changed the path of the beam. So Thomson hypothesized. His hypothesis was that the beam was a stream of charged particles that interacted with the air in the tube and caused the air to glow. Well, that's true. And then he observed that the beam was repelled by the negatively charged plate while also being attracted to the positively charged plate. In other words, the beam had a negative charge. His evidence was basically no matter what metal Thomson used for the disc, the particles produced, they were identical. The particles that had about 1 over 2,000 the mass of the hydrogen atom, which is the lightest atom. So these particles were subatomic particles. Okay. He concluded that the particles in the beam had a negative charge because they were attracted to the positive plate, and he hypothesized that the particles came from inside the atoms, because of those reasons. So Thomson revised Dalton's model to account for these subatomic particles. The atom has neither a positive or negative charge, but there must always be some positive charge in an atom. An atom is filled with positively charged mass of matter and has negative charges evenly scattered throughout. So one description in the textbook talked about a plum in pudding. You could also think of like chocolate chip ice cream. So the chocolate chip ice cream, most of the ice cream is just ice cream, and then there's little chips spread out throughout it. You could think of that as the chips are negatively charged particles, which are spread evenly through the mass of a positively charged matter, like the vanilla ice cream. So the vanilla ice cream is like positively charged, a lot of stuff, and the chocolate chips are like little negative charges, which would be like the electrons. So next is Rutherford. Rutherford had some contributions. In Rutherford's model, all of the atom's positive charge is concentrated in the nucleus. So we use the Niels Bohr model for most part, and it's been taught to you, but this is trying to show you the evolution of that process, right? We know that things are small. The small things make up other things. Then we realize that we can prove that these small things exist. Then we realize that these small things have a charge, right? And they must be balanced most of the time, but you can make something be negative or positive. And then Rutherford is saying, look, most of the positive charge is concentrated in the nucleus of this atom. Okay? So Ernest Rutherford designed an experiment to find out what happens to alpha particles when they pass through a thin sheet of gold. The alpha particles are moving fast, and they're positively charged particles. So based on Thomson's model, Rutherford hypothesized that the mass and the charge at any location in the gold would be too small to change the path of the alpha particle. Okay, so he predicted that most of the particles would travel in a straight path from their source to the screen that led up. Okay, so he thought, well, Thomson's model behaved in a certain manner, and he thought that maybe the mass and the charge at any location in the gold would be too small to change the path. Right? So let's take a look at this. So he had a source of alpha particles here, and it would go through a slit. In other words, the slit only allowed so many particles. It was a narrow space. And then when those particles hit the gold foil, this is what he saw. He saw that some of it was deflected this way. He saw that some things actually passed right through the gold here. He saw that some things bounced back here. He saw that some actually got deflected sort of and bounced all over here. And so if you're looking at the gold atoms, if it's a very, very thin sheet of gold, you would expect most of these things to go straight. The alpha particles to kind of go straight through with maybe a little bit of variation, right? But in reality, what was happening is these alpha particles were hitting these very dense parts of the particles, which was the nucleus. And so if they hit the nucleus of the gold atom, it would drastically change the path of the alpha particles. Does that make sense? Now, the reason he used gold foil is because the gold foil was a solid. In other words, it was a fixed position. And that's why he got very repeatable. Not repeatables, I don't know if that's the right word. But you could clearly see that some things were being deflected and some things were going through and some things were not. Okay? So alpha particles whose paths were deflected must have come to another charged object. The alpha particles were positive when they came close to the nucleus of the atom, which is mostly positive charge. They were deflected, okay? The closer they came to the nucleus, the greater the deflection. So, however, many alpha particles passed through without being detected. These particles didn't get close to the charged object. So an atom is almost like this, like when you think of order of magnitude, think of an alpha particle being like a meteor floating through space. Could a meteor float through our solar system and not contact a planet? Yeah. But what happens if that meteor gets really close to the sun? It's going to interact with the sun because the sun is so massive. This is the same thing. These alpha particles, most of the atom is condensed in the nucleus, but the electrons are spread out a little bit. And the electrons are so small, the probability of these alpha particles hitting an electron are very small. So they could literally pass through the gold foil, right? However, if they hit the nucleus of one of the atoms, then that's where you run into an issue. It'd be like a meteor hits Earth. Every once in a while, a meteor will hit Earth, and it has an impact on the path of the meteor, right? So it's a similar thing. Thomson's model did not explain all the evidence in Rutherford's experiment. So now Rutherford proposed a new model. He said that there are positively charged, the positive charge in an atom is not evenly spread out through the atom because it didn't have an impact on these positively charged alpha particles. He said that the positive charge is concentrated in a very small area, central, the center part of the atom. The nucleus of the atom is dense, positively charged mass located in the center of the atom, which is part of what we believe today. So let's think about this. The Houston Astrodome occupies more than 9,000 acres and seats 60,000 people. If the dome were a model of the atom, a marble could represent the nucleus. The total volume of the atom is about 1 trillion, 10 to the 12th power times the volume of the nucleus. So they're just saying that it's densely, remember we did density? The majority of the mass is in a very small location in the atom. So there's a lot of space in the atom itself. And so real quick, we'll just go over these real quick before it's time to go. Actually, no, we're not going to go over it. The bell's going to ring in a second. Are there any questions that you guys have for me?